It's a great pleasure to introduce the final speaker of today, Azat Gainutdinov, who will speak on a deformation of quantum groups and their tensor categories.
Thank you for the introduction and thank you for coming. Right, I'm going to talk about deformations of tensor categories. It will be slightly more abstract talk than the previous one, but anyway, it will be about quantum groups essentially, deformations of tensor categories. Let me begin with some motivation. So, and for me, tensor category, it will be some linear category over some ground field K. So I denote my tensor category usually C. So what it is? So C, it's a linear category, as I said. It's equipped with a bilinear tensor functor from C plus C to C. It's just product, right? But just having product of objects is not enough. This tensor product should be equipped with associator, right? It's a family of isomorphism. So this is associator. It's a part of the data of tensor category, associator. We have also tensor unit, and we have left and right unitors. So this is data we have. So these are unitors, left and right. Okay. So what we are going to do, and I'm going to deform this structure. But what kind of deformation we are going to do? So this is going to be fixed. I'm not going to deform category. I'm not going even to deform multiplication or tensor product. This is fixed. This is also fixed. So this data is fixed. But we're going to deform associativity constraints. So this we are going to deform. So we are going to deform associativity constraints or associativity isomorphisms. Okay. Right. Let me give you some motivation why we're interested in this type of deformations. So one motivation is coming from for me the first motivation is to deform in general, deform repetition categories of VOAs. So I have a VOA, it's a tensor category. We know there are some associators, and I would like to explore how many deformations given VOA repetition category admits, and especially coming from log CFTs. So from this perspective, RCFT, for example, rational CFT, are not interesting. Because there will be no, I mean, I will mention that there are no deformations of the type I'm going to discuss. So from my perspective, from perspective of deformation theory, I'm going to discuss rational theories are not interesting. So we would like to deform repetition categories coming from log CFTs. So the other motivation is to recover rep UAs as deformations of some nice categories coming from Hopf algebra theory. So H mod or H some nice Hopf algebra. So on this side, my associator constraints are basically trivial, basically identity maps from Hopf algebra. And as we learned in today's first talk, the associativity constraints are very complicated. For example, the rigidity question was discussed by Robert. It was related to studying associativity constraints coming from Knizhnik-Zamolodchikov equations. So on this side, associators are quite non-trivial. On this side, it's trivial, but I believe that at least in some cases, we can recover these categories as deformations of something nice and simple. And the third motivation, it is just fun. To deform various things, and it's a nice game, and I will give you some examples of deformations of categories of small quantum groups. So it's just fun. It's nice. Okay, let me move this side, And we're going to give you later a precise definition of these deformations. Right, and actually, another maybe motivations, maybe number 4, also quantum groups, right? Quantum groups appear in this context. Drinfeld, Jimbo, topological quantum algebras, UHG for G semi-simple Lie algebra. So these objects you can understand, or the category representations of UH. Okay, let's start this way. We can start with UG mod. So it's just category of basic representations of this semi-simple Lie algebra, where associativity constraints are trivial and coproduct is just as for Lie algebra. And what Drinfeld observed is that we can deform associators, and we can recover a category equivalent to UHG mod. This is a very particular type of deformation. It's called Drinfeld associator, and it comes from analysis of monodromy properties of solutions of Knizhnik-Zamolodchikov equation on 3 points. Let me reformulate this. This is related to the famous Drinfeld-Konov theorem. But let me maybe write you a precise formulation. This is categorical. If you want, this is categorical formulation by Drinfeld of Drinfeld-Konov theorem. The formulation is the following. Okay, due to Drinfeld, that braided tensor category UHG mod is equivalent to another braided tensor category, braided tensor category of trivial deformation as algebra of trivial deformation. So I take UG and work over here. This guy is defined over a ring of formal power series in H. So I take an universal enveloping of G and consider formal power series with coefficients in UG, and look at the category of representations. So from the algebra point of view, it's a trivial deformation, right? However, equipped with a non-trivial associator. As I say, coming from monodromies of solutions of Knizhnik-Zamolodchikov equation, the form of the associator is quite non-trivial. I'm not going to reproduce it, but so this is Drinfeld's result, right? But it teaches us that we can understand quantum groups from categorical point of view via just standard Lie algebra. Everything is nice. Coproduct is Lie algebra coproduct. It just has to be equipped with non-trivial associator, and it admits non-trivial braiding. So if you want, basically, we started with a symmetric category for Lie algebra representations, and deform associator introduced this Drinfeld associator such that it admits non-degenerate braiding. So, right, or if you want, say differently, equivalently, right, UHG mod is braided tensor equivalent to a quasi-Hopf algebra. So it's a quasi-Hopf algebra based on UGH, right? So delta epsilon co-unit and coproduct, the standard Lie algebra coproduct. However, there is this non-trivial coassociator, Drinfeld's coassociator coming from Knizhnik-Zamolodchikov equation, and R matrix of the very simple form. So it's just some exponent HT over 2, where this T is just some symmetric 2 tensor. So the R matrix has very simple form in this presentation. However, all the complexity is in the non-trivial coassociator. Okay, this is just to show you that, to tell you that it's an interesting problem to deform associators, because, for example, one can understand quantum groups from this point of view. Right, maybe I'll start here. So what is associator? So associator, it's a family of, so we're going to deform associators, right? So, but I have to tell you what is associator. It's a family of isomorphisms.
You pick the articles first and you find the phi that fits it, or you find the phi?
Yeah, you're right. It's you fix the R matrix and then you find phi that. Yeah. Because the R matrix comes from KZ2. And when you want to extend it to say breakgroup representation on 3 points on 3 tensor products, you cannot just use this R matrix. So with trivial associator, this will not make you quasi-triangle structure on this. So and then Drinfeld found this associator. So with this associator, you can construct the representation of the braid group on nth tensor product, and it's equivalent to braid group representation coming from the R matrix of the Drinfeld Jimbo. That's a theorem.
Excuse me.
Yeah.
Then this associator is not unique. There are many corresponding to this.
Yeah, there are many, but up to twist it's unique. So Drinfeld proved uniqueness results. Okay. So what is an associator? It's a family of isomorphisms. So I have objects UVW triple, and I multiply them this way. And in the algebra, in the standard associative algebra, we would say when I multiply 3 elements, they just equal, right? But in category, it's better to ask that they just isomorphic. But you don't want to ask them just isomorphism. You want some coherence conditions on this isomorphism. This is required by the fact that, for example, if you have longer words and have some bracketing, say from the left, and you want to construct an isomorphism to same word but with bracketings every on the right, there might be many ways to do that, and you want that they are all equal. And this is guaranteed by pentagon equation. So this family should satisfy the pentagon equation. And let me write this pentagon equation. So I start with all bracketings. I will also, for simplicity, omit the tensor product symbol. So I start with multiplication of UV W and say, okay, let me maybe I will just do, okay, anyway, UVW and then some X, right? And I want to end up UVW and X, and I want to end up in bracketing this way. So this bracket I don't need. Right? And there are 2 ways, 2 natural ways. So one way is I first do the bracketing. Sorry, this side. I first do the bracketing UVW. So it's alpha tensor identity, right? So I don't touch X. I just rebracket here. So what I will get U and V and W brackets here and then X. So what I can do now, I can think as VW as one object, and I can rebracket now on this side. So what I do is just U, and now VW and X, right? So I applied alpha on the components U, VW, and X. I'm almost here, right? So what I can do, I can just I don't touch U, but I can rebracket this thing. So it's identity tensor alpha. And alpha with components V, W, and X. So all this is as a mode. What I could do now, I could think about UV as one object. So I can just apply alpha, UV. So it will be UV, and now brackets WX. And I'm almost there. So what I need to do, I need to think about WX as one object. And right. And it's again alpha with different components. And right. So WX is one object, and I get to this. So what we in pentagon equation we require that this path equals this path. So that the diagram commutes. That's the only equation we require for alpha. Of course, plus naturality. Plus naturality. So this family of isomorphisms should be natural. Okay. In general, it's hard to solve these equations. So the idea we are going to linearize them. So the idea of deformation through linearization. So let me assume for simplicity that the category I'm going to deform is strict, that associators are identity maps. And I'm going to deform such a strict category. So we'll assume that alpha is of the form identity plus what linearization means, identity plus some epsilon times A. such that epsilon square is 0. So we're going to look at infinitesimal deformations. Epsilon is now a small parameter, and A is just any morphism from it's a family of maps U, V, and W, and because I assume it's strict, so it's from U, V, W to itself, to U, V, W. And let's do linearization. So let me just rewrite this equation. So this diagram I can write again. I will just write again. Identity X tensor alpha. What was it? Identity. So the last term was alpha VWX, VW and X.
I'm sorry. I'm a bit confused. Is epsilon what? Is epsilon not a number? What is epsilon? Because
It's a formal parameter. Epsilon is formal parameter. We are going to extend scalars of my category. I'm going to extend them to the ring of dual numbers. So my category in the end will be extended. It will have coefficients in the ring of dual numbers.
Okay.
Okay. So epsilon is a formal parameter, and it will be. So after we understand such type of deformations, we will ask, can we extend them to higher order or to all orders of epsilon? Yeah, okay. Let me write down that equation. Right. So what I have then alpha, what I had U, V, W, and X, and then composed with alpha on U, V, W tensor identity X, right? So this is the first path. And this has to be equal to, right. The last thing was alpha, what was it? U, V, and WX, right. WX, and the first was U, V, and W and X, right? So this is my pentagon equation, and I just plug this and that into this, and you get a linear equation on A. So what we get a linear equation. We get let me call it three-cocycle condition, condition or equation on A, on this part. So let me introduce. Okay, I will give you maybe on. Let me see if I can give it here. Right, let me write it this way. So I get some, I will write it some D of R, because eventually we will see differential. D of R equal, let me write it this way, D0A minus D1A plus D2A minus D3A plus D4A. And this equals to 0. So this is three-cocycle condition. I'm going to introduce all these DIs. Right. Sorry, yeah, right. There is no X, right? This is U, this is X. Right, right. Good. You follow. So let me introduce these DIs of A, and DIs of A, they will have 4 components. So they will act on U, V, W, and X. And so it will be with this form. So it will be identity. So if you plug, you will see that all these terms I'm going to write, they appear. So the identity U tensor, you apply, sorry, your A on V, W, and X. So this is for I equals 0. If I equal 1, you just apply A on U, U tensor V, and then W on X. If I is 2, you multiply in the argument of A second and third, and if I is 3, we do same third and fourth, and if I is 4, we apply A on the first 3 arguments and do nothing on the fourth. Okay, so the pattern is very clear, I guess, right? And this is what I call three-cocycle condition. So all these combinations, alternating sums, it has to be equal to 0. This is what you get if you just, very simple exercise, if you just plug in this with this condition into pentagon equation. You get this linear equation. And to solving these linear equations is much, much simpler. And there is actually a homology theory behind it. So there is so-called Davidov-Jeter homology theory that controls let me write this star solutions to star. So this is similar to standard infinitesimal deformations of associative algebras. It's similar to Hochschild theory. So recall in Hochschild theory, we are interested in infinitesimal deformations of the multiplication, and the multiplication will also deform first in this form, like it should be new multiplication identity plus some new bilinear map, and associativity constraint on the multiplication gives you three cocycle condition for infinitesimal, two cocycle condition for infinitesimal part. And in Hochschild theory, you are interested in deformations of algebra up to isomorphisms, right? This is a Hochschild complex that controls such equivalent classes of deformations. That second Hochschild cohomology classifies you infinitesimal deformations of multiplication up to isomorphism of certain type. Here a similar story that I'm going to write you a Davidov-Jeter complex, chain complex, such that it's a third cohomology, because here is three cocycle, and the fact that it's three cocycle, it comes from the fact that we have three arguments, right, for the associator. For the multiplication, we have two arguments. That's why it's second Hochschild cohomology for multiplication. For associativity constraints, it's third one. And classification of infinitesimal deformations up to certain type of tensor equivalence will be classified or controlled by third homology of this Davidov-Jeter complex.
Is this related somehow to the homology of the fusion ring? Or I mean, not the fusion ring.
Yeah, it's related. I will go into that. Yeah, it's related, but more tricky. Let me go here. So let me first introduce you. Give you. I think I have time to give you a formal definition of the deformation. We call them Davidov-Jeter deformations. So these type of deformations appeared in like around 96, 97, independently in works of Alyosha Davidov, and in the work of Jeter. They appeared independently. So they were starting, or at least they introduced a theory for this type of deformations. Let me give you a precise definition. So we are interested in the category, right? We're interested in the category C, tensor, and alpha. And for simplicity, alpha is identity that we're going to deform. About unitor axioms, I just ignore them for the moment. And so we're going to pass from C, we're going to consider, and let me write R is, so I have, okay, just for some field K, so K epsilon over epsilon square. Okay, so in general, I can actually consider any power n, up to any power n. So, let me introduce a category CR, which will be kind of an out of trivial deformation. So it's very simple. It's just we just extend scalars. So objects as in C. So we don't change objects, but we change home spaces. So home spaces in this category CR between X and Y is just by definition home in category C, X, Y, and I just tensor over K because this is a K module, sorry, over my ground field with R. So I just multiply with R, okay? So I extend home spaces. And also you can check that this is, it's not hard to check, that this will be our linear tensor category. So we use tensor product on objects and extend tensor product on morphism spaces or morphisms by R linearity. So CR is now R linear tensor category. I should say monoidal because I see nothing about rigidity and monoidal categories. Okay. So definition, first order or infinitesimal deformation of my triple C tensor and alpha. Okay, in this definition, I don't need to assume alpha is identity. Is a linear tensor category CR. Let me distinguish it from the trivial deformation, just CR twiddle with underlying. So it should be a linear tensor category with underlying category CR and tensor product CR cross CR to CR and associator some alpha twiddle. So I had alpha, now I have alpha twiddle. Yeah, let me continue here. That is reduced to alpha mod epsilon. Right now it's simple. Okay, CR it has tensor product essentially as C, and alpha lives in these external home spaces, but it lives in a sense in degree 0, right, where there is no epsilon. And now I'm saying I call it deformation. It's a new category with same underlying tensor product, but associator might contain now epsilon, but it should reduce to original alpha mod epsilon. In other words, for every, so I have alpha twiddle, x, y, z, it lives in this home CR, x, y, z to x, y, z, which is right. And there is a projection map, there's a surjective map to original home C, right? Just send epsilon to 0. So this is the original surjective map, and under the surjective map, this alpha twiddle should go to alpha. So this is a definition of infinitesimal deformations, a formal definition. Now a theorem. Okay, no. First, I have to introduce you this the complex, the David-Theater complex. So David-Theater, I will denote dy complex. For pedagogical reasons, we can introduce it for every C, but for simplicity, I assume C is strict. So formulas are simple. So what are cochain spaces? So the complex I denote C dy. So the cochain spaces in this is in my complex for a given category C. They are natural and the transformations of certain functors. So I denote them identity tensor n to identity tensor n. So what is tensor n? Oh, sorry. What is identity? It's identity on C. So identity tensor n on C. It's a functor from C cross n. So I take the Cartesian product of n copies of my category C and assign it to C. So what I do, this functor does very stupid thing. It just, you take n tuple of your objects and you just multiply all of them. Okay, so this is this functor. So for example, if n is 1, it's just identity. If n is 2, you just take a pair and you multiply, right? And you can see that cochain spaces are natural, just linear inner transformations of these functors into itself. Okay, and differentials dn, I will write in the form. Okay, let me write. Okay, dn is from Cn dy to Cn plus 1 dy. So differential is like this, right? And
linear natural transformations or something.
What?
Like multilinear natural transformations or something.
Yeah, but no linear, because the target of the function is just C, right? Yeah, of course right. Yeah, the porting that target C. Right. And so from Cn to Cn plus 1. So let me define components. So let me define components. So I take F, which is natural transformation identity C, right? But the natural transformation is defined by its values and components, right? So so the components, they are in the target, oh sorry, in the source. So Dn of F, it has actually okay, it has n components, but the value should be in n plus 1. So Dn of F should have n plus 1 components. So I denote them from x0 to xn. And this is my definition of the differential. So the new natural transformation from power n plus 1 to n plus 1 is just identity on x0, tensor F, and you evaluate F on x1, xn, plus there is some bulk part. We start with x0, and we just multiply I minus 1 component with I component, and take all the others, right? And the last term will be minus 1 to the n plus 1 F x0 xn minus 1 tensor identity xn. Right. So this is differential. You can check that dn plus 1 composed with dn is 0. So this is not that hard to check. And what we have here, it's an example of the thing. So what we have here is this condition I can write as d3. So what I was denoting on top of it. So d3 of A is 0, right? Because it's just indeed this alternating sum, and indeed every term is what we have here. So there are two boundary terms with identity on one side and identity on the other side, and there are bulk terms where in natural transformation you just plug in, multiply the objects, and it looks very similar like in Hochschild theory, right? Yeah, the only problem that it's typically, if you give me tensor category, it's hard to calculate actually, because first of all, to calculate cochain spaces is quite hard. In some examples you can do that, but in general it's very hard. It's very hard problem to do some explicit calculations. Let me give you an example. Okay. No, I first have to formulate theorem. First I have to formulate the theorem, and I have formulated here. So I gave you definition of these cross-order deformations, and now the theorem due to Davidov theorem, Davidov Pieter, around 97, that first order deformations of C, the way I introduce them here, are classified by H3 dy of C. Let me introduce here. So we have a complex, and I will denote cohomology of this complex Hn dy of my category C. So these are dy cohomologies, or Davidov cohomologies of the tensor category C. And first of the deformation, they are classified by H3 dy of C up to soft tensor equivalence. Soft tensor equivalence. What soft means? Soft means that underlying functor is identity. Underlying functor of equivalence is identity, right? But it might have non-trivial monoidal structure. So this theory classifies the infinitesimal deformations, but up to this type of equivalence. Of course, we want up to any equivalence to classify, right? So, and we have an extension of this. We have extension of this theorem in the work with Faitg page, myself and Christoph Schweigert. It's in 2022 that that on H and dy we have action of the group of tensor of equivalences of C. Right, so you can introduce symmetry, group of symmetry of your category. It's group of tensor of equivalences of C, and you can show that it acts on these cohomology spaces. And so the first order deformations are classified. So I will just take all these words are classified. So the first order are classified by orbits. So up to any R linear tensor equivalence, R linear tensor equivalence, classified by orbits of this action, by orbits of this action.
A quick question.
Uh-huh.
So the soft equivalences, are they classified by the second cohomology with the Rieter cohomology?
Soft equivalences.
So this kind,
Yeah. Soft. Actually, yeah, right. The second derivative cohomology, it classifies your monoidal deformations of identity functors. Right. Up to any monoidal isomorphism. Right. So it tells us that okay, the theory is interesting because you just need to study. You need first to calculate the cohomologies, and then you need to study action of these groups on these cohomologies. And it tells you about all possible non-equivalent monoidal deformations in the sense of deforming associators. Okay, let me give you an example. Say this again.
Is the soft equivalent different from an equivalence which reduces to the identity mod epsilon?
The identity, no, the functor is not identity mod epsilon. The functor is actually identity. It's different, yeah. Functor is identity, but its monoidal structure is identity mod epsilon. But anyway, it's a sort, right? But I would like to do classifications up to any linear equivalence, and the action. I mean, the variety of orbits tells you what it is, what are deformations. And we are going to study this variety of orbits. And in the case of small quantum groups, they're interesting varieties. But let me give you an example of these David-Oketer cohomologies. There are quite a few examples, but the very example which is related to the problem of Knizhnik rigidity. So let's take C, which was discussed many times in this program in the lectures of Dima Nikšić. For example, I take C as G-graded vector spaces. G is finite group. Finite group. And I look at complex vector spaces graded by this finite group. So what will be H and dy for such a category C? It will be just group cohomology. It will be nth group cohomology of your group G with coefficients in group trivial G module, but as a group is C+. So this is it's not difficult to show, and this it's always zero. And the interesting it's important to distinguish this group with another group homology with coefficients in C, but with respect to group structure with respect to multiplication. Okay, and in general, this group is not zero, and this group classifies monoidal structures, on vec G. All right. So we know that vec G admits many monoidal structures, as many as the rank of this group, right? But the Pieter theory tells you that the cohomology is zero. So why it's so? Because here we are interested in infinitesimal deformations. If you want, we look at the tangent space to variety of all possible deformations. And for finite group, this group is finite. So we have only finitely many monoidal structures on this category. And tangent space is trivial. So we have no infinitesimal deformations. So what this theory is sensible, so this Davide-Pietra theory is sensible to categories that admit continuous family of deformations. That's why it's interesting, because basically the cohomology detects if the category, whether the category has continuously many deformations or just maybe if cohomology is 0, you cannot say much more. There might be deformations in this sense, like discrete deformations, but so it detects continuous deformations. As I said, the calculations are extremely hard. Even like for examples like Taft algebras, for Hopf algebras, there were no calculations till recent. So what we did, it was my work with Christoph, first work with our student Jonas Haferkamp. We extended the theory to the version with coefficients. They're right here. So the first step was to understand better the theory. In like 2019, joint work with Haferkamp and Christoph Schweiger. So we extended dy theory. We extended it to dy theory with coefficients. So it's similar to Hochschild theory, right? So in Hochschild, remember that the coefficients are bimodules. And here, the coefficients are, so the coefficients, they live in Drinfeld center of category C. So the coefficients are in Drinfeld center, okay? And I will talk about H and dy. So it will be for the category C, and for some coefficients U and V, and the U and V, they live in the Drinfeld center, okay? So there is a pair of coefficients. You can reduce it to one coefficient, but it's important, it's useful to have a pair. Anyway, so we have such an extension, and let me formulate the result. So the problem, okay, going back to Hochschild. So the analogy with Hochschild cohomologies is quite useful, because in Hochschild, you know, these cohomologies, they are, so in Hochschild, let me write this, in Hochschild, when you calculate HHM, you know that they can be written as extensions. So there is also a coefficient, it's algebra A and some bimodule M, right? So it's an extension group in the category of AA bimodules from A to M, right? And it is extremely helpful, like because instead of doing calculations with a complex, original complex, you can just calculate extension groups. And for dy theory, such a homological result was not known, and this is our theorem. So we provide homological formulation for this dy, or if you want extension theory for dy homologies. Let's write the theorem. So this again was what I mentioned, where I mentioned. Same people, FGS, Page, myself, and Schweiger in 22. So the theorem says that HM dy of C with coefficients U and V, so it's isomorphic to nth extension group in the Drinfeld center of C, but relative to C between U and V. Okay, so in particular, HM dy of C is just nth extension in Drinfeld from the tensor unit to itself. So it's self-extension of tensor unit, but relative to the category C. And unfortunately, I have no time to explain what relative means, but believe me, like standard homological algebra results apply. So for example, you have your nether product, this has, for example, your nether product, and which means that we have a natural algebra structure, great algebra structure on HM dy. You have a fundamental lemma property which tells you that for example, calculating nth cohomology, you just need to take projective resolution for tensor unit. It's in this case should be relative projective resolution, but this is something you can actually study, and what we did in examples. You can construct these resolutions explicitly and do standard calculations in homological algebra. And maybe so what I want to say that they think it's much easier to calculate than the original definition. Okay, and let me give you maybe some examples. So the example, the interesting example, I will take restricted quantum group. Let me start for simplicity for the case Q equal I. So what is this as algebra? It has e square f square 0, and it has a Cartan k to the 4 is 1, and standard relations of quantum group, standard coproduct that you know from the quantum groups. So this is a 16-dimensional Hopf algebra, right? And so the theorem, again of the same people, that's Hn dy, H3 dy. So we are interested in deformations. Okay, maybe formulate like this: H1 dy in this case equal H2 dy equals to 0. H3 dy equals to c cubed. So infinitesimal deformations up to soft tensor equivalences is a 3-parameter family. And H4 dy is also important. H4 dy tells you whether there are obstructions. So here there are no obstructions, which means that every deformation you have, you can lift to higher order. And now the group, in this case, the group of tensor after equivalences of this category of C. So C is now this category of modulus over this algebra. It's just torus, so it's just C star. Okay, and so the orbits of this, if my group G of G action, orbits of G action on H3 dy. So this is what they classify. This should be 3, sorry. Right, because the third homology classifies. So the orbits of G action on H3 dy for this restricted quantum group form a complex variety CP1 cross C. So we have two complex parameter of actual honest deformations, and none of them are equivalent to each other. So they are alinear, non-equivalent alinear deformations. We have as many as these. And we have some results for other roots of unities. It's important if root of unity is odd, or 0 mod 4 or 2 mod 4. The results are different. And I can give you maybe just finish. So just in these particular examples, we know explicitly bases here. It's I mean like a particular base element is something like 1 tensor E, tensor EK. Plus there is some alternating combination when you move this E in different tensor components. So it's actually quite simple. The basis here is, at least in this example, is quite simple, and we can explicitly write representatives. I mean, like associators for every point on this variety. We can just write explicitly. And due to the result that H4 is 0, it can be lifted to basically any order. And unfortunately, I cannot tell you. Another interesting question is how many of them admit, for example, braiding. This I cannot tell you because my deformation doesn't control the braiding. But at least it's for me. Yeah, I think it's first real example that because again, this category is also closely related to the symplectic fermions, as we know. And this example shows that this category admits continuously many deformations. Okay, thank you.
Very much for the talk. Do we have questions?
In the example you did with the group G,
Yeah.
it seems that this dy homology just depends on the Grothendieck ring of the category, right?
Yeah, that's actually
It's a general picture. You expect maybe for the semi-simple case.
Yeah, right. I mean, you don't change Grothendieck ring, right? Because you don't deform tensor product. Grothendieck ring will be the same. You don't change category, you don't deform tensor product. So
this is something that just depends on the ring. not of the, I don't know, the net.
What do you mean? It depends on the ring. Yeah. No, okay. No. It's not depend on the ring. Yeah. It depends on the structure I deform. Right. So I believe it could be different monodromy categories with the same within ring, but having different homologies.
Yeah, but in this case, it's just
No. In this case, yeah, this is a particular example of Packiana rigidity. By the way, about Packiana rigidity, let me comment that with this result, it's quite easy to prove Packiana rigidity, because if C is fusion category, Drinfeld center is fusion, at least in characteristic 0, and such extension will be also trivial, because if this category is semi-simple, then relative extensions are also trivial. So it's easy way to prove Packiana rigidity. Okay.
Yeah, very interesting. So more like a comment. In some recent paper with Thomas, because of the deformations, the stuff you like also, we classified what are all the tensor structures. If you fix the tensor product, what are all the tensor structures on this small quantum group if you have an induction factor. So if you have and the result is that there is a CP1 variety of possibilities, and only one of them is braided. So what I think is interesting, maybe lay next to each other, I think the CP1 somehow.
No, but it's different stories, right? First of all, you fixed associator, right? Your associator was fixed. No, look at your associator was fixed.
No, but you want to find all possibilities what the associator could be.
Right.
And you see that there is one parameter family. Basically, you fiddle with this EF relation.
Yeah.
And one of those choices gives a braiding and the other don't. But we assume that there is another module factor. So I think that's the second factor. So I think there's like two different sort of things that can go wrong, and one of them we assume trivial. And so then
I don't know. I have another opinion, but we can discuss. I have different opinion. Okay.
All being 0 means it's unobstructed.
Yeah.
So the unobstructed in the sense you can extend to a arbitrary powers of epsilon.
It's complicated. It's actually a silicon problem. We showed. Okay. So this theory is actually secretly a theory for deformations of functors, tensor functors. So H2 of a functor. I mean, there is such a complex for any tensor functor, right? And for example, second homology, it indeed classifies you all monodal structure on infinitesimal deformations of monodal structure for a given functor. And then abstractions live in H3. If H3 is 0, you can leave infinitesimal deformation to any order for functors. Okay. For this category, there is no such a theorem. And with Mathieu of H, we showed that if H4 is 0, you can certainly lift to order 2 and 3. So, but the story about associator deformations and lifting to any order is much more complicated than in Hochschild theory. But for Say again? Yeah, for Toshtival with sub you say it's subtle. No, I mean for associative algebra, if third homology of Hochschild is 0, the result you can lift it to any order. Yeah. I mean, how to lift? I mean, find representatives is some work, but you can lift. So basically, if abstractions are trivial, your infinitesimal from a given infinitesimal deformation, you can lift it to a formal deformation, like in all orders. What is subtle if whether it's global deformation? Yeah. Okay. Yes. Strictly speaking, we have a theorem that it can be lifted up to order 3, but I believe it can be lifted to any order, every order. Yeah.
You say the abstraction for the second and deformation is finite, so maybe you can get the infinite series of the deformation.
Yes. Yeah, this I don't know. Because I don't even have example like even to find in second. I mean, I would need to. I mean, this is very recent result, so it's an interesting problem. For example, to lift it to second, third, and understand. It's actually quite complicated, but it's not clear. Yeah, it could be that some of them are not convergent. Yeah, but what I believe is that at least there are some points which corresponds to actual logarithmic symplectic fermions. We know they are described by quasi-Hopf algebra with same coproduct, but non-trivial coassociator, and they admit on degenerate braiding. So there are some points in this variety.
One last question, otherwise David is killing me.
My question is, If you start with a candidate grading, for example, the truncation of the exponential of Casimir, you mentioned.
Yes.
Can you refine your theory to study the appropriate deformation, the associator which would match this starting grading?
Yeah, you're basically asking if there is a Knizhnik-Zamolodchikov counterpart of this story. Yeah, I don't know. I didn't study. I was asking myself these questions, but it's probably possible. But such a theory is not known.
Okay, I think further questions we have to postpone to discuss afterwards. Thank you again.
Are all of these ones?
Huh?
Are all of these ones realizable completely? Like